So let's prove this lemma. So again, we choose x in x and y in y uniformly at random. And before that, we have x and y where the x1 is at least size x epsilon plus times x, and y1 has size at least epsilon times y, and its density between x1 and y1 is far from, at least epsilon away from the density between x and y. And again, as before, let g be the random variable. With density between xi and yj, where ij are chosen as x is in xi and y is in yi. Then again, as before, the expectation of g is density of xy, and expectation of g squared is n squared over xy, where the energy of this refinement. Then now what we want to do is we want to try to measure the difference between this. As we mentioned before, we always know that this is bigger. So this is always bigger, but we want to show that this is bigger than this by certain amount. So that's what we want. So that's exactly, before we show that this is actually bigger than this. So that gives us the conclusion that the energy is not decreasing. But here we want to show that energy actually increased by a certain amount. So we want to show that this is bigger than this by a certain amount. So the difference between these two is actually variance of this random variable. And then from above, this is actually this, because this is same as x, y, n squared q, x, y. So this is what we have. But what does our choice say? So this variation is actually the expectation of this. So let's try to analyze this. Variation, variance, not the variation. Variance of G is actually expectation of this. So which is what we know. So let's try to see how this, we want to show that this has a large value with certain probability. But what's this? This is the xi and yj minus the density between x and y squared. But if we choose well, then we get, if x is in x1 and y is in y1, then we get this. In this case, what's our assumption? We know that this is our assumption, so this is bigger than epsilon squared. And then this happens with the probability at least size of x1 times size of y1 over size of x times size of y, which is bigger than epsilon square. So if you take the expectation of this g minus epsilon g square, this is always positive, always non-negative. And then with probability this much, it takes this. So this is bigger than epsilon to the 4. So variance of g is expectation of this g minus expectation of g square is at least epsilon to the 4. So this is at least epsilon to the 4. So you divide this on the both sides, then you get this inequality. Maybe you delete the equality here. Yeah, and this is strict inequality. So you conclude this. Now, so this is only for, dividing one set into two. Then, for given epsilon regular partition, it has many parts, and we might have to, take the further partition in each set. So let's prove that we can actually improve this further if this is not epsilon regular. So if a partition of the vertex set of graph G is not epsilon regular, then there exists a refinement Q of P where every Pi is further partitioned into at most 2 to the k parts such that the energy increased by at least epsilon to the 5. So this is roughly what we want to do. Our idea was that we take certain partition, and if it is not epsilon regular, we take a refinement. And then our function, energy, goes up by epsilon to the 5. But one thing that I didn't mention, I forgot to mention, is that by definition of our energy, it's quite clear that this is never above 1. Because always, so this is m most 1, and then this, once you sum up, that's also m most 1. So it's less than 1. So if we prove this lemma, then we can start from a partition which is not epsilon regular. Then we take a refinement. Then energy goes up by a certain amount, and then we keep do that. As long as this is not epsilon regular, we can keep do that. But at a certain point, we should not be able to do it further because it cannot go above 1, but every time it increases by this much. So at most, 1 over epsilon 5th time, or before that, we are stuck. At that time, we must have an epsilon regular partition. So we are, so it suffices to actually prove this lemma. So how do you do it? It's for all ij. For specific pair, this lemma already tells us how to deal with that specific pair, but there could be many pairs. So for ij such that bi and bj is not epsilon regular, we find, say, aij inside bi and aji inside of bj such that, which that witness the irregularity. And let Q be a common refinement of this P by all those sets Aij, meaning that you have a partition P, and then between these two you have to take this part, and between these two you have to take this partition, and between these two you have to take this partition, and between these two you have to take say this partition. Then you take the partition into 1, 2, 3, 4, 5, 6, 7, 8 parts here, and 2 parts here, 4 parts here, and 4 parts here. And then, that's your common refinement. Then each Vi is partitioned into at most 2 to the k parts, because for each I you have to take j from 1 to k, and then each time you might have to partition into 2, so each part is partitioned into at most 2 to the k parts. And let Qi be the partition of Vi given by Q, where P is say V1 to Vk. Yeah, we already have said that. Then the energy of Q is summation of all Qi and Qj, the energy between them, where Ij is, pairs in K. This can be partitioned into 2, where this Qi and Qj are epsilon regular, or Qi and Qj are not epsilon regular. But what do we know? Before we show that, where did we? So for certain partition, no, not this. So once we take a refinement, the energy never goes down. So that will take care of the first term. So this is epsilon regular, and then it's further partitioned. That means we don't know how it will change, but we know that this is at least as before. And then this is not epsilon regular. It's partitioned into many parts, but those parts is a refinement of this A, Ij, Bi, and Aij, the remaining. This part, and then Aj, and Bj minus Aj. So this is actually, so Qi, Bi, and Bj are partitioned into, this Aij, and then remaining, Aj, and then remaining. That's how we take. And then because of others, so Vk and Vs, because of this other, it's further partition. Because of this other, this is further partition. So our partition is actually these 4 sets. But what we know is that because they are not epsilon regular partition, there was this green partition. And then this final partition is a refinement of this green partition. And then we just show that if 2 partitions are, one is refinement of the other, then refinement has at least as large energy as the original one. So this is refinement of this, so you have this inequality. And what we have just shown is that this is okay. So you take all Bij or all Ij. And then each of them, we just show that there is a increment. Because they are not epsilon regular, we have this increment, which can be written as summation of all not epsilon regular, Ij not epsilon regular, epsilon to the 4 times V I, Vj over n square. But what was our definition of epsilon regular partition? We said that it is epsilon regular partition if Ij not epsilon regular, and we add this, and then this is smaller than epsilon, then it is epsilon regular partition. So here we assume that this is not epsilon regular, meaning that this is bigger than epsilon. So this is at least the original energy plus epsilon to the 4 times epsilon, so epsilon to the 5. So which proves the lemma. Now we prove the regularity lemma. So we start with a trivial partition. And repeatedly apply the previous lemma. Each time the energy increases by at least epsilon to the 5, and it cannot be more than 1. So this terminates in at most epsilon to the negative 5 times, and it yields an epsilon regular partition. And number of parts we get, it only depends on epsilon, not the size of the original graph. So in each step, the number of partition is from k to, k times 2k. Let's say it's at most 4 to the, k to the 2, 2 to the 2k. So you do this many times. In each time you have this. So let's just write it as this is far less than 2 to the 2 to the k. Then, you do this every time your height increase by 2 in the tower, and then you have to do this many times. So you show that the final partition has a size at most tower of 2 times epsilon to the negative 5. And one can ask that maybe this proof yields number of partitions at most this, but can we do actually better? Maybe it's a flaw of this proof. Maybe if we have a better proof, can we get a better number? But Gowers in 1997 proved that it is somewhat unavoidable. That means he showed that there is a certain constant C such that for all epsilon positive, there exists a graph G which satisfies the following. Any epsilon regular partition of G has at least, this tower of epsilon to the negative C many parts. So with better proof, this minus 5 could be improved, but it's still tower of a polynomial depending on epsilon, so which is still a huge number. So this shows that this number of parts cannot be really improved too much. So this is the last video of the last lecture. As this is the last one, let's end a bit early. So yeah, for this semester, thank you for following this course and then enduring all the difficulty of the homeworks. And yeah, due to the coronavirus, the course was taken online, and then it caused lots of difficulty. And then thank you for the enduring all those difficulty, and then enduring also this lecture of me. And yeah, I hope you can also do the remaining homework well, and then also you do well on the other courses. Yeah, thank you for listening all these lectures. Thank you.